Hi Chemistry Kids, so today we're looking at how we get energy from food, reading food labels and the kind of equations they might throw at you that you have to use. So what this is I'm on the right page on my study design. So we're on the very last three, and in one lesson we're going to cover two. So we're going to look at the comparison of energy values in carbs, fats and oils and proteins. Why I said it in the wrong direction, I don't know, because I can't read. And then we're looking at glucose as our primary energy source, including balanced thermochemical equations for cellular respiration. I'm going to include a couple more because they're in the textbook and it seems silly to not include them, but not in here. But I think if you glean from what we've got. So that means Thursday and Friday we'll be working on this last one, and then we will be done. We'll have done all of the content in some way, shape or form. Some you might not remember, some you might want me to go through again. That's perfectly fine. But that's our last three, looking at the energy content of food. Jack Plus, it is chapter. One day we're all super organised, and chapter 13. So it's chapter 13. And then I think there's the last chapter, which is about stuff. So this is about it's about reading food labels and what it tells us about foods and how we use it in the body. It's very, very complicated how we use it in the body, so we have to just use general figures. How you might burn energy might be very slightly different to somebody else, but these are, standardized numbers. This is not a food technology course, it's just a chemistry course. So we have different amounts of components of food. So whatever food we're looking at, bread, crackers, chocolate, donuts, are going to have different amounts of fats, carbs, proteins are three main things. They'll also have things like water, which won't provide any energy, fibre, which will go straight through us, so it doesn't count towards our energy, or have vitamins that you no longer have to worry about. It's got all this other stuff. So the energy content is the amount of heat energy, either in joules or kilojoules, that's produced by burning 1 gram of that substance. So that's how we get the energy content. It's not quite the same in your body as it is there, but it's pretty close. So it's close enough for us to use those values in terms of what we're looking at. 1 calorie, so we use joules in Australia, but you will see calories used a lot, especially if you're looking like American diets or British. We use calories, I think, when we're looking at food. 1 calorie is 4.184 joules, which I don't think I ever really made that connection. I think I thought it was 3. So everything is not as bad for me as I thought it was, which is good. So if you know calories and you get something in joules, you just kind of have to divide it by 4, and that's how many calories it's going to be. But there's all kind of issues with calories or whatever. So our food, any food we're looking at, is a complex mix. It's a complex mix of different sugars, carbs, fats, proteins, vitamins, fibres, water, sodium, what else would be in there? Minerals, all sorts of stuff is in our food. So we can't use mole because it's going to be too much of a complicated mix. But we can calculate a general amount of energy we get from our food. This would be lots of work for lots of people over many years to make specific numbers. We're going to just do a rough kind of using our data book. So fats give us the most energy, then proteins, then carbs. How do I know this? Because they are telling us in our data book. So number 13, fats and oils. The heat of combustion as them is 37 kilojoules per gram. Protein, 17 kilojoules per gram. Carbohydrates, 16 kilojoules per gram. So if I'm burning these, heat combustion gives me this. So you can see that my fats and oils are giving me twice as much energy per gram, or over twice, as my carbs. So That's why we try and avoid some of these foods, too much fats and oils, because the amount of energy very often we put into our body is not the same as what we need, so we end up with storage. So when we're looking at this kind of question, I don't want you to completely forget that we use our food for other things. So we use proteins for muscles, we use fats for our brains, we need to have a certain degree of fat for nerves, we need them for controlling other stuff, for things. So yes, we use them for energy, but we need them for other things as well. So if they throw a weird bit in there with you on this bit, I need you to have that kind of in the back of your head. So we're calculating energy of my noodles, so which I didn't bring in here, but this is actually from some packet of noodles. So I've got a packet of noodles with a serving size, which is normally about 30 grams, and I look at the instructions on the back to see how terrible they are for me. So fats are 14.6 grams per 100 grams. My carbs are 63.6 per 100 grams. And protein is 9.9 grams per 100 grams. So I want to work out, if I eat 100 grams of noodles, how much energy am I getting? And then I might even convert it to calories. So first, I get my data book, and I've got fats is 14.6. This times by 37. And I don't make a calculator. I'm sure I should probably be working this out by hand. 14.6 times 37. Though I would suggest you really don't work out too much by hand, because why would you want to? Keep it simple for yourself. I see lots of kids, even ones who are very good at maths, make a simple mistake because they've done it in their heads. Kind of do a bit of both. And my old maths teacher would have killed me for saying that, but yeah. Then we've got 63.6 times carbs is 16, which gives me 16 gives me 0.6, and then protein is 9.9 grams, 0.9 times 16. I should have done it in the order that they had it here, would have made my life 17. Yeah, that's why you do it in the order they give it to you, makes it much easier. Protein is 17. Oh my god. And that's in kilojoules per gram. Right, so I just add those together, plus 1.6 plus 540. So that's my 1726 kilojoules. I think that's about a third of my daily allowance, maybe. I don't know what my daily allowance is. Not that kind of person. And then my calories. So we gave you the calories here. So I divide that number by 4.184. And it's 412.5 calories, which I do know is about a third of my daily allowance. So one packet of noodles, if I ate 3 packets of noodles ish, so if I ate 100 grams of noodles, that's my calories. So it's just, I don't think this is overly complicated. I'll post some videos, other videos doing it, but I don't think this is overly complicated. It's just saying we've got this kind of complex mixture. It's made up of these different things. Use these values to work out how much energy we're getting for our foods. Then we've got some equations. So this is our 2 dot points going through. So we've got some complicated, well, we've got some equations and we'll just need to break them down into their components and remember how to do our balancing. So I think some of you might have to do some balancing practice over the holidays. Maybe these fats is a good way to start. So any fat, we're just looking at this kind of combustion reaction, and it's going to be exothermic, which means that we have a negative delta H. I'm not including that here because I wanted to give myself some room to show my balancing. So I've got C17H31 COOH, which is in here. That one that I'm not going to say. Oh, that one, linolenic. What are big ones? I can't see. Linolenic. Double bond, 2 of them. So nice balancing needs to go on. So first way we start, 17, 18 carbons. So we've got a carbon dioxide here, we've got 18 here. We're not going to add any more. So we're going to just have 18 here. That means we've got 18, 40, 38 oxygens. And then we've got our oxygens up here that we need to add. And we've got hydrogens as well. Might leave this here. Do our hydrogens. We've got 31 hydrogens. And then we need some extras in to balance these oxygens here. Oh, 32. That's what I paid attention. 32 hydrogens. And some hydrogens here. 32. 32 divided by 2 is 16. Helps work in maths. 16. Why have I got O2 there? That's oxygen. I was wondering, why am I doing hydrogens up here? It's down here. So we've got combustion because we've got this, and our water, oxygen, giving us carbon dioxide and water. Ignore that. These silly mistakes I'm making. Please learn from my silly mistakes. Right. So can't be adding any more hydrogen, so I've got 16 hydrogens here. Then I've got 32 here. I've got 16 here. That gives me a total of, oh, and minus 2. So I've got 2. I'm making this more complicated than it needs to be, I'm sure. 38 plus 16, 54. Here, but I'm taking away 2 because I've got 2 here. So that means I need I've made a mistake somewhere because that's 25 and I know that because I know it. 25 gives me 50 plus 2, 52. Oh, it's because I did maths in my head. Don't do maths in your head. It messes up. 52, take away 2, gives me 50. And that gives me 25. This is a game of practice. And knowing where you're ending up. So then you spot your silly mistakes. So this is combustion. And this is going to be the same for all of them. Just with our balancing out. So start with the carbons. Then with the hydrogens. Then fill in with your oxygens up here. kind of 3-step process. Make sure you don't do maths in your head if you are likely to make silly mistakes like me. Right, so carbohydrates. This is the one that's the actual dot point, but we have to include fats because I feel we have to include fats. So we get carbs, we eat our carbohydrates. They're either stored as glycogen that goes back to our carbs and becomes glucose, or they go straight to being used as glucose, and that's where we're getting our energy from. It's called cellular respiration. We do this in year 10, maybe year 9, and you did in biology, cellular respiration. So when you see cellular respiration, you know that it is an exothermic reaction where we end up with carbon dioxide, water, and lots of energy that we can use. So aerobically, which means we have water, we have oxygen with O2. We take our sugar, use aqueous, this is a gas. So we're breaking down our sugar in the presence of oxygen to give us carbon dioxide, water, and lots of energy. Remember, delta H, when it's negative, means energy out. Don't forget this. I'm going to suggest, without even looking at it, that's a thing that gets missed by lots and lots of students. It's the kind of thing I would miss, so that's why I know. Then anaerobic respiration. So this is when we don't have any oxygen. So it's either happening in our muscles when we're working hard, or fermentation, which is either bread making or alcohol making. Both of which use yeast, generally. There's probably ones that don't, but keep it simple. So we take our glucose, C6H12O6, or potentially maltose or whatever. They're all kind of the same. And, I mean, this wouldn't be happening in you. And then we're breaking it down to lactic acid, which has this formula here. And because of this end, we have an acidic end, and that's what gives you that stitch when you're working out too hard. Then we have when we're making alcohol or bread, again we've got our sugar, but we've got no O2, no oxygen. So it's been broken down into this alcohol and carbon dioxide, which is gas. So this is what you see when you're like brewing or making bread. You'll see that bubbles of gas, and you'll see this kind of fizzing, which is that and that kind of coming together. So that's that. 2 dot points, which I think are pretty easy. Well, pretty easy. It's just, again, with a lot of this unit, it's about remembering and finding a way to remember this stuff. So that, you don't need to remember those numbers because you get given them. These ones you do. You have to know how to look that up. You need to remember this. You need to remember that. And you need to remember that. Okay, so that's that 2 dot points. One more to go about calorimetry and calibrating and working out scientifically how much energy we have.